Alright. Oh, gotta set up the camera. Okay. So, the plan for today is to do 1 or 2 Leetcode questions, followed by 1 or 2 lessons from the Odin project. And this time going through HTML and CSS as opposed to just React. So I'll be backtracking on the Odin project a bit, just to learn through HTML and CSS again. And I'll be doing some scheduler development. During that time, I might also try and set up Tailwind UI to be saved in a private GitHub repo. So, yep, probably get started, to be honest. In my time offline yesterday, I did set up Alacrity and NeoVim properly, so now it should all work on my Windows computer at least. So WSL is starting. Let's see. Find minimum in rotated sorted array. $153. Okay. nums. See an example here. Find min. And I probably want to print that. Res equals something. No, let's just do that. And let's have a look what we can do here. Alright, before I continue, I'm just going to quickly be right back. Okay, I just gotta organize something real quick. I'll be like less than 10 minutes. Okay. Let's try and solve this. You're given an array of length n, which was originally sorted in ascending order. Has now been rotated between 1 and n times. For example, the array was sorted might become 3, 4, 5, 6, 1, 2 if it was rotated 4 times. 1, 2, 3, 4. And if it was rotated 6 times, notice that rotating the array 4 times moves the last 4 elements of the array to the beginning. Rotating 6 produces the original array, assuming all elements in the rotated sorted array are unique. Return the minimum elements of this array. A solution that runs in O of n time is trivial. Can you write an algorithm that runs in log of n time? Modulo three, 1, 2, 3, 4, 5, 6. So I think the hint that they're giving here is notice that rotating the array moves the last 4 elements to the beginning, right? And rotating the array 6 times produces the original array. The mod of 6 rotations is 0 when the length is 6. The mod of three, 4, 5, 6, 1, 2 is just 2. So 2 and 6, the last digits in both of these signify how far we are from the start, I suppose. If you look at the last digit, you can't compare it to the highest digit there. And if you just look at that digit, keep on going left, this is still going to be O of n if I try to look anywhere left. So if you got 2, you move that to the front. Only if. No, it's still going to be O of n. While you do rotations yourself. If you look at the first and last, maybe 3 is greater than 2, you flip them. 1 is greater than 2, you flip them again. No, you couldn't. So maybe you compare the first and last. So what are the things you can make about this? So the nom's length has to be greater than or equal to 1. So you can say compare the first and last values. If they're the same or greater, you know there's going to be a problem. Compare the first and second last value. Why do you want to compare the first and second last value? Can't you just do another rotation? Compare the 1 and the 3. One and the 2. 2 is greater than 1, so you move 1 to the front. And then you'd have a binary. You'd have a sorted array. But why would we want that at all? You want to return the minimum element of that array. So you compare 2 and 3. You shift that. You compare 1 and 2. You don't do anything. Well, you know 1 is smallest number there. Or could you just binary search it? Say half position is 5. 5 increments. Oh, well, you know 5. This is not binary search. This isn't binary search.
Hey everyone, welcome back.
Okay, let's have a look at the solution. I mean, I say it's not binary search, but this whole section is binary search, so I don't know the solution, basically, is what I'm saying.
And let's write some more neat code today. So today let's solve the problem, find minimum in a rotated sorted array. So we are given an input array of length n that is sorted in ascending order, but it could be rotated 1 to n times. For example, if we have an array like 1, 2, 1, 0, 1, 2, right? To rotate it by 1 basically means to take the rightmost element, move it to the beginning like this, right? So this has been rotated by 1. We could also rotate it by 2 by taking the last 2 elements and moving them to the beginning. So something like this, right? This has been rotated by 2. And so we want to find the minimum value, and we want to do it in log n time, as they say. The good thing is that we do have some kind of sorting property that we can use to our advantage to find this log n time solution, and we are guaranteed that every value in the array happens to be unique. Of course, it would be easy to find a linear time solution, basically just scan through every single value in the array and then take the minimum value and return it. But we can use the sorting property to our advantage even if the array has been rotated. Let me show you how we can do that solution. As you might be able to guess, it is going to involve the binary search algorithm, which is usually the algorithm that runs in log n time. So the fact that the array was originally sorted is what hints to you that binary search might work in this case, but it's not going to be a traditional binary search. Now, of course, if the entire array was rotated n times, that basically means we took a sorted array such as 1, 2, 3, 4, 5, rotated it n times, basically leaving it in the original sorted order. Now, if we had an array that was completely sorted like this one, an easy binary search would work on a sorted array, but if the array is fully sorted, then we know that the minimum value is going to be the leftmost, right? So if at any point we get binary search is going to run like this, a left pointer and a right pointer. If we ever get to a point where the entire array is sorted, we can just return the leftmost element, or at least consider this as being the minimum value. So let's try a binary search and see how it's going to be different than a regular binary search. Now, of course, we want to find the minimum value. We're going to initialize our left pointer here and our right pointer here. Basically, the current pointer situation means that we are considering this entire array to find the minimum. The minimum could be from anywhere in this array. And the result is going to be the minimum, and I'm going to keep track of that over here. Now, of course, one way we could do this problem is basically find the pivot, right? Find the position where, the elements are not in increasing order, right? From here to here, 3 to 4, they're in increasing order. From 4 to 5, they are in increasing order. From 1 to 2, they're also in increasing order. But from 5 to 1, they're in decreasing order. This is the pivot, right? So basically, this value is going to be the minimum. But I'm going to do it in a slightly different way where we don't necessarily have to, look exactly for the pivot. I'm going to take, left, right, take the half of them, get our middle pointer. Our middle is going to be over here at 5. So I'm going to consider as 5 being the minimum value we have seen so far, right? So our result is going to be 5. Now we have to ask ourselves, okay, this could have been the result, but now we don't want to, look at this value again. So the question becomes, are we going to search to the left or are we going to search to the right? Where are we going to find the minimum value? Where are we going to find a value that's even smaller than 5? Well, first consider this. Since we rotated the array, we have two portions of the array that are sorted, right? We have this portion of the array that's sorted, the left portion, right? And we have the right sorted portion of the array, which is also sorted. So the question is for us, with this middle pointer, at this value 5, are we currently in the left sorted portion or are we currently in the right sorted portion? Now, if we are in the left sorted portion of the array, don't we want to search the right sorted portion? Reason being, if we rotated the array, the left portion is always going to have values that are greater than every value in the right sorted portion, right? Because when we rotate, right, suppose an array like this, we're taking the rightmost value, the largest value, and putting it over here, right? So we're taking larger values, putting them on the left side, right? So therefore the values on the right are going to be smaller now. So that's why it's always going to be that way. So if our middle pointer is currently in a value that's in the left sorted portion, then we want to search the right sorted portion because it has smaller values in it, right? So how can we know if we are in the left sorted portion? Well, like I said, every value in the right sorted portion is going to be smaller than every value in the left sorted portion. So one thing we can check is if the current middle value is greater than or equal to the value all the way at the left of our thing, right? Because the left value is going to be the smallest value. If the middle value is greater than or equal to the leftmost value, that means this middle value is a part of this left sorted portion, right? In which case we want to search to the right. Now, if our middle pointer, suppose in this case we can see 5 is greater than or equal to 3. The reason we're doing greater than or equal is technically this middle pointer could actually be at the left position as well. That's one edge case. And in that case, we would also, this would be the left sorted portion. But suppose our middle pointer, instead of being at 5, was actually over here. It was at 1. What would our condition evaluate to then? Nums of middle would be 1. Is that greater than or equal to the left value, which is 3? It's not, right? Because the values in this right sorted portion are going to be smaller than the left sorted portion, in which case this would evaluate to false, right? If it's false, that means, if we're at a value that's in the right sorted portion, then we want to search to the left, right? Because in this case, the right, if our middle was at this, it makes sense that, okay, all the values to the right of it are going to be greater. So then we want to search to the left. But obviously these values are also greater, but that kind of doesn't illustrate the point, because what if our middle pointer was over here, right? Maybe we had some values over here. This is where our middle pointer is. We see 2. Okay. 2 could have been the minimum. Then we want to search to the left because we want to find even smaller values. Particularly, we would want to find this 1 that happens to be smaller, because we don't know where the pivot is. The pivot could be here. The pivot could be here. It could be anywhere. We just know we have to look to the left if we want to find smaller elements. If our middle pointer happens to be in the right sorted portion, then we want to search to the left. If our middle pointer is in the left sorted portion, then we want to search to the right. And I just showed you the condition we can use to detect that. So now I'm going to run through the example and it'll probably make more sense. And by the way, the algorithm I'm describing only works on a rotated sorted array. If we ever got to a point where let's say our right pointer was over here, meaning that, this is our entire search range, then we could not do this algorithm. In this case, if we ever got to a portion of the array that's completely sorted, we would just take the leftmost value and see if it's smaller than our current result, and then we would stop the entire binary search. Okay, so now let's run through the example. These are the conditions that I talked about that we're going to be using. So our middle pointer is here. Let's check we checked that this might be the minimum. Now we're never going to look at this again. So now we're going to check, is this value greater than the value all the way to the left? Yes, it is. So we're going to search right. Since we're searching right, that means we're never going to search these values again. So we can cross them out. We're going to take our left pointer and shift it to mid +1. So our left pointer is now going to be over here. This is our new search range. And as you can see, this portion of the array is already in sorted order, right? How do we know that? Because the value at our right pointer is greater than the value at our left pointer. So that means that the array is entirely sorted. And then we can just take the leftmost value here, which is 1, see if it's smaller than our current result. Yes, it is. So then we can return 1 in this case. Now, just to kind of illustrate the opposite case, arbitrarily, I'm just going to say our middle pointer is actually going to be over here for some random reason.
I think I pretty much get it, so let's just do it. Left and right pointers. So we got a left of 0, a right of the len of nums, while L is less than equal to R. We gotta have a result initialized to I guess infinity, math_inf. Or I think this works. No. No, okay. Nope. Yep, there we go. Okay, it's good. Maybe I can just do that. Hello from Turkey. Keremken Ozcool. Nice to see you. Nice to see you in the chat. Thank you for joining while I solve this question. Okay. L is less than R. Eventually we want to return the result. and L is less than R, our condition is to check if the midpoint, so M is equal to L plus R minus L, div 2, if the num of the midpoint is greater than or equal to the nums of the left pointer if that's the case, what am I doing? Okay, if that's the case, then you search, so you know that the midpoint is in the left side or in the rotated side. If it's in the rotated side, don't do anything. And look to the right side. So then your L pointer is going to equal to the midpoint plus 1. Else your right pointer is equal to mid minus 1. And let me think, would that be right? So if it's the middle point is the same as your leftmost, is greater than or equal to the leftmost, then you move the left pointer forward to m plus 1, and then if that's not the case, you move the right pointer to m minus 1 because you know you want a smaller number. Okay. Kerem Can says, I need to write some code too. Good luck. Thank you. Good luck to you too. Have some fun. Hope you have fun writing. Okay. What else would there be? Yes, so if we got to take this m value as the highest value or the smallest value. Okay. And Rm minus 1 no else res, he said that the res would equal to nums of the leftmost? No. The right and left. Right m minus 1. So if you do that movement, that would mean you would have a sorted array in that subsection. And then if that's the case, how do you check that? L is m plus 1. But before this, I'm just taking a stab. Res nums L. That kind of makes sense. Else, if you go to the right side, type float is incompatible with int. I don't think I can make this an int, an infinity, an int. I don't think. Oh, what am I typing? Darn. Do I have Python even? Yeah, I don't have Python even. I'm just gonna copy this. Hold on. Shift V. 19 G. Yank. This is probably not gonna work straight away. I have a feeling, because there's a lot of cases that I haven't even considered fully yet. Hello. Insert. Control V, I guess. I know there's a lot of cases I haven't considered yet. Inf is not defined. Yep. Yeah. Well, that's because. Yeah, can I convert inf to an integer? That's fine. So your output return nothing. Or the second case, you return 0. But for the first case, yep, okay, so let's consider now more closely examples. So 3, 4, 5, 6, 1, 2. If you go L and R, L has the 3, R has the 2. 0 to 5, 5 minus 0 is 5. Div 2 is floor divided, so it becomes 2. And you got L is 0, so it's gonna go 0, 1, 2. It's gonna end up at 5. So if it ends up at 5, we look at this 5 and compare that to the 3. Since this 5 is greater than the 3, we know the 5 is on the rotated side, or how Leetcode said it's on the left side, although it's confusing to say it that way. Technically I would call it the right side. So alright, let's say it's the right side, alright, by my definition. So it's on the right side of when it's completely sorted, no rotations. This 5 is on the right side. So sure, 5 is on the right side. You know that every value to the left is going to be smaller than the 5, but not exactly the smallest. You know that to the right of the 5, there's a chance to get even smaller numbers. So for now, from what you know already, the 3 is the smallest. So you first set 5 to be the smallest, sure. And then you realize if nums m is greater than or equal to nums l, then the smallest would be the 3 here at the moment. So then you'd put that 3 down. And then you'd move, so that 5's there, then you move the left pointer to the 6. So the left pointer is at 6, the right pointer is at 2. The midpoint would be right minus left, which in this case would be, so 3, and for 5 minus 2, 5 minus 3 is 2, div 2 is 1, so from position 3 plus 1 is 4, so you know it's going to be the middle point there. Sure, that's no problem. And then you add that to be the smallest number, and you look to the left and see if it's a number greater or if it's a number smaller. You see that it's a number smaller. It's a number greater. And because it's a number greater, you know that this 1 is on the left portion under my definition of what left means. So it's on the left portion of the sorted array. 1, 2. And the 6 is on the right. So 1 is on the left. Alright, so else then r is equal to m minus 1. So the midpoint being that minus 1. So you got 2 left and right pointers on the 6. And then the 6, if this is the case, the min of that L is going to be m plus 1, and then you'd terminate from there. But this 1 here, this 1, we do this calculation. Yeah. But technically this calculation might be able to go within this for loop. So that might be. And the fact that I don't have an output here. Okay, it's because we got errors. Index out of range for this M value. Why would that be, right? Index out of range for this thing. This M. If we have... Okay. List index out of range. So M is still index out of range. The midpoint of two of the same div0 is just L. You gotta print what M is. Three, 5, and 6. 3, 5, 6 becomes 3. So 6. Is that right? R minus L. Oh, right. Okay. This has to be minus 1 here. Yep. Damn, bro. I did it. Okay. So that was a good question to consider. If I just did it like this, would that have also solved, would that have also passed? It would have. So looking at what I had before, it was pretty much right despite the int that I did to the infinity, because you don't need the int on the infinity, and I was just doing typing checks, like why do I even care about that? And otherwise, like, it would have been fine regardless, but it was probably more efficient to do this, marginally more efficient to do it like this. And then it was just this bug that got me. Okay. What else? What else? What else? What else? I think I'm good. I'm just gonna change it here as well. And let me just double check my eyes over this. Yep. Okay. I don't need to follow conventions of typing get commit messages, but I like to do it anyway. 153. Gosh darn it. Git commit. Alright, fine. It's probably because it's a new file, I think. What was that? Okay. Did I use HTTPS URL? Okay. I'll be right back. Sorry, my nose was dripping because it's so cold in my house. Okay. Valid. I know why. So I face the exact problem. Okay, so follow the SSH URL, git remote add. If you get fatal remote origin or residence, then you have to use set URL. Yeah, obvious, because this is, I made a public repo for this. So I'm not surprised that we got problems here. Yo, password. You need my password for that? Okay, I'm not going to type out a password. Need to use git, not this. Fix that problem. This occurred when I cloned using HTTPS and try to push changes. However, when I use SSH to clone, this problem didn't occur. In case you already cloned this repo using and don't want to redo everything, you might set URL. Okay. Git remote set URL origin git at github.com username okay. Sorry, I'm just that was a huge cough. That was a loud cough. My bad. The people in the comments here who don't know the reason why, I'm talking about, like, this person is saying, okay, but why does this occur in 2016? Yay, okay, done. So that was that question. Let's finish watching.
See how our binary search would work in that case. Well, we would take this middle value, say that it might be our result. So our result is going to initially be 1. And then we're going to run through these conditions. Is the middle value greater than or equal to the leftmost value? It's not. So we execute the else case, which basically means we're searching left, right? So we're going to take this is not going to be considered again. We're going to take our right pointer, set it to mid -1. So our right pointer is going to be over here, and we're going to cross out 2 because it's never going to be searched, right? Because we shifted our pointer. This is our new search range. Once again, you can see that this range is sorted. Basically, the left value is smaller than the right value. So this is already sorted. We can take the leftmost value over here, see, is this smaller than our current result? It's not. So our result stays the same, and we don't have to search this entire portion because it's already sorted. So that's kind of the general idea of how this algorithm is going to work. It's pretty easy once you kind of figure out these two conditions. With that being said, we can jump into the code. Okay, so now let's get into the code. As I mentioned, we are going to be maintaining a result. Now we can set this to some arbitrary default value. I'm just going to set it to nums of 0. We could just pick any value.
I just want to copy and paste this.
Value in the input array nums, but I'm just going to choose the leftmost just because.
Okay,
we're also going to have our 2 pointers. Initially, left is
Okay, I'm back.
It's going to be all the way at the left at index 0. Right is going to be at the rightmost index, length of nums -1. And we're going to keep running our binary search while our pointers are in a valid position, while left is less than or equal to right. And like I mentioned, if we ever get to a subarray that
I suppose you never need res
already
nums to be anything but a number within the array, so infinity was kind of overkill. Never really needed it.
sorted, basically if the value at the left is less than the value at the right, then we can update our result potentially, setting the result to the minimum of itself and the leftmost value of this sorted portion, and then we can break out of this while loop. If the array is not sorted, that's when we're actually going to be doing our binary search portion, so we can compute the mid pointer, basically left plus right, integer division by 2. And with this mid value, we're going to potentially update our result, setting the result equal to the minimum of itself and the value at the mid pointer. And once we're done with that, now we want to know, are we going to search to the left or are we going to search to the right? So how can we determine that? As I mentioned, the condition we want to know, is this mid value a part of the left sorted portion? It is a part of the left sorted portion if the value at the middle index is greater than or equal to the